But why are we going to discuss Lie groups and Lie algebras? Why is this important? So why? A course on Lie groups and Lie algebras. Anybody has any idea why you are here taking a course on Lie groups and Lie algebras? What would be the physical significance?
Just because we have a gauge theory, we need to know the properties of a gauge group.
Okay, very good. So somebody said that they will play a role in gauge theory. But more generally.
They are symmetries of forces.
Excellent. That's the key word. Symmetry. Okay.
Right?
Yes.
You have your mic on? Yeah, so, okay.
It's on. Yes.
Okay.
It's on. Is there a problem?
So they cannot hear you, so maybe.
So maybe you should move the mic up.
Higher.
How about this? So is there any way you can tell? Oh, you're getting emails from people somewhere else? Okay, okay. This is fancy. And you're watching it. This is a little bit, yeah, I have to confess it. The problem is that now I cannot make jokes of people and make fun of people who are not here because you never know who's going to be watching. Yeah, so this is going to be a little bit, yeah, I have to remember that. Okay, so where were we? We were talking about symmetries. Now, you might say, probably you have learned that symmetry is a very important concept in physics and that we can learn many things. We can constrain things using symmetry and that we can simplify problems using symmetry. But in fact, I could say that most of the things we know in physics follow from it. Okay? So in what sense? Well, we could even start with the basic symmetries that we see in nature, which are related to the Poincaré transformations. Okay? Do you know what Poincaré transformations are? No?
Transformations and translations.
Very good, very good. Yes. This is just a fancy name. I mean, well, it's not fancy, it's the name of somebody. But it's a name for the combination of two things that probably you know very well. Lorentz transformations plus translations. Okay? What most people don't know, okay, at least when you're learning about Lorentz transformations and translations, is that they are so powerful that they can actually tell us the kind of particles that we can see in nature. Okay? Just by studying what this means and the structure of these symmetries, we can understand that the nicest ways to classify particles is by using their masses. In fact, it gives a definition of what mass means. It will tell us for massive particles, it will tell us that we can also use another number, which is called the spin. For massless particles, it will tell us that we can use a number that is called helicity to classify particles. When we take the massless particles, which, by the way, we believe nowadays that most particles that we see in nature, at least in the standard model, at high energies, are massless. Okay? So this is not a very strange case. Back in the 60s, people thought that the only massless particle was the photon, and that the photon was a weird thing, and that massive particles were the most important things. Nowadays, we know that somehow it's the other way around. Most particles in the standard model are massless, and there is only one guy floating around which is massive, which we still haven't seen. Which one is that guy?
Higgs boson.
The Higgs boson. And I thought that I was going to wake up this morning and had some news that the Higgs boson had finally been discovered. There is a conference going on right now in Mumbai. But it turns out that still the Higgs is a little bit tricky to find. So the news wasn't there. Okay? But we believe that the Higgs is a particle that is massive and the particle that provides masses to all our other frames, which are leptons and quarks. Okay? Here on the massless sector, we have gauge bosons. Now, it turns out that if you just use quantum mechanics and you combine all these with symmetries, with this symmetry, you can constrain so strongly the way massless particles can interact that you can just purely from symmetry, from Poincaré group, you can deduce that these particles, at least for helicities plus minus 1, who has a helicity plus minus 1 and is massless?
Photon.
Particle that you know.
The photon.
The photon, yeah. Who else? Have you heard of any other massless particles floating around, which you cannot actually see because somehow they become confined every time that you try to, yes?
Gluons?
Gluons, excellent, yeah. Whoops. Gluons and photons. Just by using that when you scatter these particles, you are supposed to satisfy a very important constraint that we believe is true, which is unitarity. Just by assuming unitarity and assuming that there is this symmetry, you can conclude that photons, well, yeah, you can conclude that gluons, particles with helicity plus minus 1, can only interact, or their coupling constants are only consistent if they satisfy a very particular property, which is called the Jacobi identity, which makes the coupling constants of these particles become elements of an algebra, the structure constants of a Lie algebra. And that's part of the reason we study Lie algebras. Okay? Now, what kind of interactions you can have, what kind of particles, how they interact, everything is controlled by symmetry. Okay? So that's the reason we should start with Lie groups and Lie algebras in any course that has to do with high energy physics or even condensed matter. If you want to think about condensed matter, symmetry is also constrained very, very much what we know and how physical processes happen in nature. Okay? So I forgot to mention something important, which is that before we move on into the actual subject, let me recommend 2 books that will be useful for this week. One of them is the book by Weinberg on quantum field theory, volume 1, just the first chapters, and the book by Georgi on Lie groups and Lie algebras. Okay? Very good. So now we can move on. And I'm going to take the risk of boring you to death, but I think it's necessary a little bit. Let's start with quantum mechanics. What do we have in quantum mechanics? We have a Hilbert space and physical systems correspond to what? A physical system is supposed to correspond to that, to what? In the Hilbert space, yes?
Array.
Excellent, array. That's precisely the correct word. Correspond to rays, okay? So we have array. Let me call it R. So what is array? Well, you can take an element in your Hilbert space and you say that all elements associated to this or related to this by a phase are in the same ray, okay? So you can think about the ray as an equivalence class. Physical systems only care about the equivalence class modulo a phase factor. Very good. What else do we have? We have an inner product. So if you're given two states in the Hilbert space or 2 vectors in the Hilbert space, we can define the dual of one of them, and then define this map into the complex numbers, and this will be our inner product. Okay? Now, from this inner product, we have the notion of a norm, which is very important, which is that this quantity for any vector is greater or equal than 0, is actually greater than 0 for any usual vector, but is equal to 0 if and only if the vector is exactly 0. Okay? What else do we need in quantum mechanics? We need observables. And observables are what? What do we call observables? Operators. What kind of operators? Hermitian operators. Very good. So let's call it A, and its Hermitian means that it satisfies this property. And what is the dagger? What is the adjoint of an operator? Well, if we have a state phi, and we apply this to psi, we can think about this as being this adjoint operator, the adjoint of A acting on psi, or we can also think about this as being A acting on phi, the dual of that inner product with psi. Okay? So the definition of the adjoint of an operator is one such that these two formulas agree. Okay, very good. So, and what do we get? What do we have to compute in order to extract physical information? What is the physical information we extract out of a quantum mechanical system? What are the predictions? And what do we compute from the eigenvalues? Probabilities. Excellent. So we compute probabilities. Very good. And so what do? Well, suppose that you have a physical system which is a ray, and we want to compute the probability of going to some, let's say that we have some bases of rays, and we want to compute this probability, we call this P, and say that the ray R is described, or one element here is described by this state psi, and say the ray Rn has this state psi n, then this probability is nothing but this overlap. Okay? Very good. So now we're ready to discuss what we want. Which are symmetries in quantum mechanics. So the simplest way to think about a symmetry in quantum mechanics is just by saying, well, if you have a physical system and you have an observer who is going to describe the system, say, by these bases of objects, and you have some other observer that is related to the first one by something that we believe is a symmetry, then the description of the physics must be the same. Well, we said that the physical information comes from probabilities, so the probabilities measured by one observer must be the same as the probabilities measured by the other observer. Okay? So if we have observer 1, which describes the system by this set of rays, and we have observer 2. By the way, you should feel free to stop me at any time, or even if you don't understand something I said, maybe I didn't pronounce it correctly, okay? So that you can use it as an excuse to stop me at any time. You can say, excuse me, I didn't understand that part. I won't be offended, okay? Or you can also tell me you just misspell a word. That can actually happen, and it will happen many times, probably, okay? So it's unfortunate that I don't have a better notation for what the observer 2 measures or sees, okay? But we're going to use prime for that. This is just prime, okay? So what's the condition? Well, what we need for observer 1 and observer 2 to be related by a symmetry transformation is that whatever they measure here, so if we have some probability, this should agree with this probability. Okay? In other words, we should have that this happens. Okay? Now you might say, well, this looks like a very interesting constraint on what symmetries we have to be, and we would like to know how symmetries, yes? Yes, yes, yes. Yes, so we are measuring probabilities, right? So these rays are the rays chosen in the basis of some observable quantity, yes.
And this is another observable.
And this is the general state of the system, okay? So you have your system in a state psi, and this is the basis of a particular observable, and you're measuring probabilities. The probability of finding your state, your general state, which is a linear combination of these guys, in a particular state, would be given by this number.
So how can I know which n is here and equivalent to n is here? Like?
Well, because we know how to translate what the operators look like in one system and the other. We will get to that soon. Very good question. Okay. So a very natural question is to ask, how are these two sets of states related to each other? Okay? This is a question that Wigner asked in the 30s already, because it was natural to think that it was a very important question. So Wigner, as a very responsible physicist, decided to classify or to study what are all the possible transformations that can map one set to the other and satisfy this property. So that's why we call this Wigner's theorem. This was around sometime in the 30s. And the theorem says that for any such transformation, there exists an operator, so we're going to call U, such that if psi belongs to R, then U acting on this state produces something in R prime. But the important part of the theorem is that this operator is either unitary and linear, or anti-unitary and anti-linear. Okay? So that's very powerful. Basically, he said, or he found, that all we have to do is to think about operators that are either unitary and linear or anti-unitary and anti-linear. That must be the ones we have to consider if we are thinking about symmetries acting on some physical system. Okay? So let me remind you what this means. We are not going to go into this, because these ones are going to be the most important for us, at least during this week. In your quantum field theory course, you will actually find some of these guys. So that's why I decided to mention it, because you will see them in a few months, I guess. Okay? So the first class. Which again are the only ones we're going to consider during this week. So what do we mean by this? Well, we mean by this an operator that satisfies this identity, u dagger u is equal to the identity. Or in other words, u dagger happens to be the inverse of the operator. In terms of states, what this means is that if we have this combination, this happens to be exactly equal to this. So now we see explicitly how the property we wanted is satisfied. Okay? And what do we mean by linear? Well, linear means that if we have U acting on some superposition of states, it's nothing but the same superposition of the corresponding states in the new space. Okay? With the same coefficients alpha and beta. These are complex numbers, but the operator doesn't do anything to these complex numbers. What do you think it happens in the case when the operator is antilinear? You get?
For
Well, what happens here?
you take the conjugate to.
Excellent. Once the complex number passes through this, you get the complex conjugate of the number. Okay? But once again, this is something that you will see in your quantum field theory course. And if you don't see it, please ask for it. Okay. Very good. Now let's make a very trivial observation. What do you think? Is the identity operator in the first class or the second class?
First.
Very good. The identity operator is, of course, in the first class. It's unitary and linear. You would say, well, how boring can that be? This is such a trivial observation that we shouldn't even be talking about this. But it has a very interesting consequence. Imagine that you have a group of transformations, or you have a set of transformations, like rotations or translations, okay, that are parameterized by continuous parameters. You can change parameters. You can define a rotation as small as you want, or a rotation as big as you want, okay? But all these rotations are connected or can be achieved one from the other by changing some parameters continuously. Now, of course, a rotation is connected to the identity. We can say, well, we simply take the identity means I don't do anything to my system. Or I can just rotate it slightly and continue, okay? So in the case of rotations, if we want to know how rotations are represented as operators in our Hilbert space, which of the two classes do you think would rotations be in?
First.
Why?
But it has to have the identity. So
Because it has to have the
it's
identity.
the limit of the smallest.
Excellent. So our trivial observation gave us a very powerful result. It says that any group of any set of transformations that are continuously connected to the identity must be represented in our Hilbert space as operators which are in the first class. Okay? So the consequence is that any set of transformations that are continuously connected to the identity must be or must correspond to operators that are unitary and linear. All right, very good. Now I kept saying, even though I tried not to, I kept saying that if you have any group of transformations, so I didn't want to say group because I want to make the following claim now, that sets of transformations form a group. Okay? And I assume that all of you are now experts in group theory, right? And you know everything that there is to know about algebras, thanks to Anna, okay? Well, no, I'm not going to assume that. I'm not because it's not true, but just because it's good to go through everything consistently. So what do we mean by this? Well, what we mean is the following. If we have a transformation T1 that takes R to R prime, and we have a T2 that takes R prime to R double prime, of course, we can define another transformation T. And here comes something a little bit funny. Sometimes we want to think about a group as something where we can define a product, okay, or a map, not a product, but a map from the Cartesian product of these two objects into itself, okay? So sometimes you want to denote this product multiplication as G1 dot G2. But when we think about transformations, we usually think about the transformation T2 composed with T1, because we want to act first with T1 and then with T2, okay? But sometimes this would also be represented in terms of groups in the opposite order. We would think about this as being the element that is obtained by saying that we have T1 and T2, okay? So just pay attention that whenever we talk about something acting on something, we want to think about the composition rule, and we will think about this as this one being first and this one next. But then in terms of the group, we can also denote it as this one first, writing it first, and this one second. Okay? So what is this transformation? Well, it's a transformation that is obtained by first applying T1, getting to here, and then applying T2 and getting to here. Okay? Now, of course, the set of transformations we're talking about will have an inverse. So let me. So there is an inverse. For any transformation we consider in the physical system, and there is an identity which is doing nothing. Okay? So those are the basic sets of axioms that something has to satisfy, or a set of objects have to satisfy in order to be called a group. So now we have that all these transformations, or the symmetries of our system, form a group. Okay. What do we do with that? We want to know how this group looks like as operators acting on our Hilbert space. Now, the operators acting on the Hilbert space, they also have a product structure. We can compose operators, act one after the other. And we would like to know if the set of operators we get by studying those transformations on our Hilbert space, we want to know whether they form a group or not. So take let's map our group of transformations into our unitary operators. We know that if we take any transformation t, we will get some unitary operator called u of t. Okay? That was our friend's theorem, which I just erased, but which you know very well by now, which gave us only two possibilities, and we're only considering the possibility where these transformations are unitary, because they are connected to the identity. Now, if we have t1 and t2, we have u of t1 and u of t2. And we can think about, as we said, the element t, which is t2 composed with t1, or t1 composed with t2. And we can think about this as u of t1 acting on some state, and then u of t2 acting on that state. Okay? Now, of course, we can construct the operator u of t2 dot t1. Do you think that this is going to be the same as the operator t2 dot t1 acting on the state psi? Very good. Very good. There is nothing that tells us that this is a question. Is this supposed to be equal to this? You might say that the answer is yes. But there is nothing that tells us that has to be the case. Remember, for this to be a symmetry, all we need to do is to map rays into rays, okay? And get probabilities right. So that would happen even if we have a phase factor here that depends on the state that we're choosing and the particular operators we're choosing, T2 and T1. Okay? Now, that means that this will not satisfy the properties we have here. Okay? Now, here is an exercise for you. I know that I have to be careful and not say homework, because homework means something very definite. But an exercise, I want to define it to mean something that you can do if you want, if you have time. Speaking of time, to keep track of time. Yeah, I realize we don't have a clock here.
Yeah, we're missing a clock.
Yeah, that would be useful. Right. Okay, here is the exercise. Use the linearity of the operator to show that this phase factor is psi independent. Okay? So show that once we apply this to any state, we're going to get the same factor. If we get a phase factor, it has to be the same for any state. Okay? And this means that we can write this relation as an operator statement. Okay? Very good. OK. So what do we want to do now? So who knows what a representation is? OK, let's see.
If we have a group, then the representation is a homomorphism to some linear group, vector space, an earlier group.
OK, very good. So let me say it in a more colloquial way. So representation would be a mapping from a group G into a set of linear operators acting on a vector space. So what is our group here? Our group of symmetries, of transformations. What is the map? Here is the map. What are the linear operators? Our U's. Okay? But as you said, it has to be a homomorphism. So we need precisely what we don't have there, or what we don't seem to have there. First, let me give a name to this map. Let's call it D. So what we need is that D of the identity, that the identity is mapped to the identity. And we need that if we have G1 and G2, this goes into D G1, D G2. OK? Or in other words, that D of G1, G2 happens to be equal to D of G1 times D of G2. Now, here I'm thinking about the elements in the group and the multiplication in the group. OK? Well, but we don't have that here. OK? Of course, if in our previous case, our phase factor happens to be 0, then we can say that we have a unitary representation of the group of transformations. Okay? If the phase factor doesn't happen to be 0, then people still want to talk about some sort of representation. So if phi is not 0, people call this a projective representation. Okay? Very good. But once again, just as we did with Wigner's theorem, here we have two choices or two possibilities. And of course, we're going to assume that we're always dealing with this case. So we're going to assume that 5 is equal to 0.
Ready? So if I define the U's to be an equivalence class multiplied by the phi, then we get a projective representation, right? Or is that what it is?
No, actually, I don't think that will buy you. No. No, I don't think you can make that definition, right? Okay. So once again, one reason I'm mentioning all these possibilities, even though we're not going to discuss them, is that in the future, when you find them, you don't come back and say, haha, you didn't tell us that there was such a thing. So you will come back and complain that I was lying to you. Okay? But that's of course not the reason. The reason is that you can start thinking about what these other possibilities are. Usually, it's a good idea to ask questions like, what are all the possibilities coming from the mathematical consistency of the theory? Why some of them are represented in physics and why some others are not? Or if they are not, then there should be a deep reason why they aren't. And those are usually questions that lead to new ways of thinking. So it's important to know that there are other possibilities. OK. So we have been talking already, informally, about Lie groups. What are Lie groups? So, well, these are groups whose elements, yeah, it would be nice. Is there another eraser somewhere? Yeah, thank you, because then I don't have to go from one place to the other. These are groups whose elements are labeled. Well, here is one case where somebody can help me. I always get confused with how many L's there are in label. By a continuous set of parameters. Okay? So what do I mean by that? Well, with Anna, you studied finite groups, right? So finite groups were groups who had a finite number of elements. So the group was a set, and the number of elements in the set was finite. Okay? These groups will be groups that, of course, have an infinite number of elements. But not only they are infinite, they are not even countable. Okay? We have a continuous set of them. So we have to find a way of labeling them. And the way to label them is by introducing a set of real parameters. Here we're going to consider real parameters. Phi. Phi, I want to think about phi as actually being a vector of parameters, or a set of parameters. We can have m of them. Okay? So sometimes I'm just going to write phi to mean the whole set of parameters. But I can also use the label phi a to refer to all of them. Okay? Now we're going to consider a special class, as we said, which are called connected Lie groups. For it to be a group, of course, it has to contain the identity. Now I want to consider only, for these lectures, groups so that every element in the group can be reached from the identity by following a path in parameter space. Okay? So that's what the kind of groups we want to consider. And what's the reason for it? Well, it's simple. It's the same reason that we used before. We want to represent them as unitary operators. And for that, we need these objects to be connected to the identity. There are groups that are not connected. Okay? Do you know any group that is not connected?
O3.
GRN.
Sorry?
GRN.
GLN? GLN is connected.
O3, for example.
Sorry?
The rotations in a three-dimensional space were non-special.
Yeah, the rotations, well, it would be, it's not strictly speaking rotations. It's the group of orthogonal transformations because there is also parity, right? We can perform a reflection, and a reflection is not continuously connected to the identity, okay? So it has several components. Inside each component, you can connect everybody continuously, but then you have to apply one of these discrete operations to send one component to the component that contains the identity. So we're only going to be talking, even in those cases, only about the connected component that contains the identity. Of course, the other ones by themselves are not groups. Why not? Because they don't have the identity in them. And that's the definition of a group. OK. And the only reason we're doing this is that, of course, we want to consider them and take unitary representations. Because after all, we're assuming that the phase is 0 when they act on a Hilbert space. OK, so here comes, let's see. You know, it would be nicer if one could move two at the same time.
You can.
Is it possible?
Yeah, the presets.
No, but no, it's,
If you go back, there's an option for you to go on the.
oh, there is
right.
another option to move two of them at the same time.
If you go to presets.
Yes.
So these are the presets.
OK.
You can move 3 at the same time.
Yeah, I want to move two at the same time.
No, new presets then.
And I want to be able to move them at different rates. Even, yeah. No, that would be useful. Yeah. OK. Very good. So what do we want to do? We want to study the structure of this. OK. Well, what do we know? Well, we know that if we take T of phi 1, OK, so some element in the group labeled by a set of numbers, which I'll call phi 1, and I multiply that with a group multiplication in the group, with a group multiplication with T of phi 2, that must be another element. But what could that be? It would be something, right, inside the group, because that's the assumption that this is an element in the group. Therefore, this is a point in the group that is labeled by some parameters that depend on the original parameters. But we don't know what it is. So it will be a function of phi 1 and phi 2. So G is a set of numbers that depend on phi 1 and phi 2. Okay? At the moment, we don't know what it is. All we know is that this must be true. Do we know any constraints on this function G? Simple observations. Well, what if phi 2 is equal to 0? Which, by the way, I'm assuming here, I'm choosing a parameterization such that P of 0 is the identity. Okay? So here, 0 here means with m entries. Okay? So what should our function G give us if we have 0 on the second entry of this function?
I1.
It should be exactly equal to phi1. And of course, if phi1 is equal to 0, we should have that is exactly equal to phi2. And if both are 0, which already follows from here, but let me just write it here for completeness, it should be 0. OK. So once again, these simple things will buy us a lot in few seconds. Now, mathematicians, when they were dealing with groups like this, they thought that it was very, very complicated to understand the structure. Because after all, you have an infinite number of objects. So how can you deal with this infinite number of objects? Well, the key to understanding monsters like this, because they look like monsters, after all, you cannot just sit and label and write the table, the multiplication table. So here is a trick. So the trick to tame these monsters was the following. Was to consider infinitesimal transformations. Okay? Well, if you cannot understand the whole object, because it's too complicated perhaps, okay, then maybe you can just start with something very simple and just go to the identity and move slightly away from the identity and see if you can understand the structure there. And hope that by understanding the structure there, you can continue and understand the structure of the whole group. Okay? So what do we mean by that? Well, we mean you take T of phi, where phi is an object that is infinitesimal. Roughly speaking, what we mean by that is that every time we see phi squared, we declare it to be 0. So in a Taylor expansion, if you wish, we only stay to leading order in phi. There is a more refined mathematical definition of what infinitesimal means, but we're not going to get into that. It's not necessary for us. So if you have our unitary operator corresponding to T, and phi is infinitesimal, then the whole idea is that we can expand this around the identity. And here is a matter of definition, but I'm going to put an I here. Okay? And say that this can only be linear in our parameters phi, and we have to sum. This is a summation. So this means we're summing over A from 1 to m. Where the TAs are operators again, right? The identity is an operator. These are real numbers. So this has to be, these guys will have to be operators. What kind of operators are they? They are?
Unitary.
OK, so who thinks they are going to be unitary operators?
Oh, no.
Raise your hands. There's only one. The other option was Hermitian operators. Sorry? Well, now there are too many options. So, OK, so let's just see what do they. Yeah. So the constraint is that our operator U has to be unitary, right? So let's see what that means. Well, if we plug this in here, we get this. If we put it here, we get this. Okay. Now we expand. Remember, infinitesimal means that I don't write phi squares anywhere. Okay? So all these formulas are for infinitesimal phi's. And this has to be equal to the identity. This cancels with this. And we conclude that this must be true for any phi's. So we can choose phi's that have all components equal to 0 except 1. And conclude that the corresponding TAs we have to be, with this combination we have to vanish. And we can do it for every single component and conclude that all TAs must be Hermitian. Okay? Well, Hermitian operators made an appearance in the first part of the lecture, right? They corresponded to what? To observables, right? Now, could it be that every single observable in nature actually arises in this form? Is what you get by doing an infinitesimal transformation on some symmetry? Well, I think the answer is yes. Okay? So there is actually a deep connection between what we think about as operators that we measure as observables and symmetry. Can anyone give me an example of an operator that is an observable?
We have momentum.
Momentum, right? What is the corresponding symmetry?
Translations.
Translations. Very good. What else?
Rotation with Lorentz.
So if we have rotations, what would be the corresponding observable? Angular momentum. So you see, it works for two cases. Must be true in general.
What about position?
What?
Position.
Position.
Yeah, what does that correspond to?
Is it maybe translations in momentum space?
Yeah, so let's see.
Sir, does it even make sense that position is conserved?
What? It's not. I mean,
No, here, remember, here, yeah.
But it's an observable.
Yeah.
Okay, okay, okay. Okay. Well, let's all think about that. So what happens to the position operator? I still stick to my position, speaking of, that the statement I made is true, okay? So let's all think about the position operator. Hopefully somebody will come out with the answer before the end of the lecture.
Maybe the shift in a momentum space corresponds to a position operator.
So you're thinking about what?
Shift in momentum space. Translation.
Shift in momentum and space. Well,
So symmetry with respect to inertial frames of reference.
let's think about it, okay? At the end of the lecture, we can discuss it more in more detail. Because, yeah, we have to move on. Okay, so let's continue and try to understand more deeply what the structure of these G's are. So now we want to consider a small phi's, okay? Now we want to go from infinitesimal to just small transformations. Well, in that case, it means that we're really doing a Taylor expansion of our operator. Of course, the leading order term will be exactly the same as before. But now we allow for quadratic terms. And this must be some operator. And we are only going to work to quadratic order. So we are going to keep order phi cubed terms as something we will discuss later. Not today, but later in the week. Okay? So we're not going to worry about these terms. We're going to do everything to quadratic order. So this is, again, an operator. What does this operator have to satisfy in the labels A and B? So this operator, TAB, better be symmetric in A and B, because this is symmetric in A and B. It's the same parameter, the same class of parameters phi. Okay? This very simple requirement is going to be very important for us very soon. Okay. So now let's look at this and try to study this relation to quadratic order. Okay? In order to do that, we will also expand G in Taylor series. Okay? So let's expand G and say A, dA. There will be a term that is linear in phi 1. There will be a term linear in phi 2. So here I'm just doing a Taylor expansion of this function, assuming that it's possible. Of course, we know it's possible from the conditions we wrote before over there. ABC, let's put a D, ABC, phi 1, B, phi 2, C. And yet another one, plus order, cubic orders. Yes?
Do you have to really plug D and the E separately? Does that combine these two things together?
Thank you very much. Yeah. Thanks. Yeah. Okay, so this is our expansion of G. What can we learn from here? Okay, so A has to be equal to what? 0. BAB has to be equal to what? Yep. And so does CAB. What else do we learn?
E and F has to be
Okay, so life looks a little bit simpler now. So that means that we can write our operator simply, our function G is order phi q. Okay? Well, that looks simple enough. If we could only understand the structure, yes?
Could you repeat how you got the last two?
We could have what?
For B, C, E, and F. How you got those conditions?
Sorry, can you say, what do you want to do?
How did you get the last two?
Oh, the last two. Yeah, very good. These last two conditions. Well, from here, you see, if I set phi 2 to 0, right, I have to get phi 1. But remember, the coefficient, this was multiplying phi 1 squared. If I set phi 2 to 0, fine, I don't learn anything about f. But then the answer will be phi 1a plus E, A, B, C, phi 1b, phi 1c. But this is not what I want, right? I want this to be exactly equal to phi 1, not to quadratic order or anything like that. So it's a very strong constraint. Okay? In fact, any cubic terms or higher order terms that only depend on phi 1 must vanish. Otherwise, this will not be true. Okay? This is the only one that has a chance of surviving, because when I set phi 2 to 0, this is gone, and it gives me only phi 1. If I set phi 1 to 0, this is gone, and it only gives me phi 2. But terms like this will not vanish when we set the other one to 0. That's the reason why we have to set them to 0 from the get-go, from the beginning. Okay? Is that clear? This is very, very important. Very good question. Yeah. So this was E, and we're setting that to 0. Okay. Well, certainly this function here, in this form, satisfies these constraints. Okay. Oh, I see. Oh, that's a catch. This is nothing. Yeah. Okay. Now we're in a deadlock. Oh, what do we do?
So what do you want to do?
No, there is not. I'm kidding. It's just that I want to show this and at the same time this one.
Move that one up.
Maybe-
Right on the
Yeah, I'll have to move up this one, right? That's the solution. Now we are stuck until that one becomes boring. Okay, so in the meantime, while I figure the blackbirds out, why don't you start expanding this relation and using the expansion of this, and from the expansion of this, plug it into the expansion of this, and tell me what the constraint on the D, where is the D? It's over there. Yeah, and tell me what the constraints on the D's are. You have almost something like 30 seconds. Well, you understand what the problem is? I want you to use the expansion. Okay? I want you to use that expansion over there for any u for a small phi. Here, apply it to u of this and u of this, and to u of this too, okay? And on top of that, I want you to use the expansion of G inside there and compare terms. Yeah, I know it looks messy, but it's nice to do it at least once. So what time is it? Okay. Yeah. Let's be brave and give it a shot. Okay. You probably all you're probably done with it, so you can tell me if I make a mistake. So this is what we want to do. And we want to compare this T of G phi 1, phi 2, all of these for the small phi's. Okay? So on this side, what do we get? We get the identity plus I phi 1a TA plus a half phi 1a phi 1b TAB. Remember, cubic terms will not be important for our discussion at this point. So okay, that's what we get on this side. So we can expand this and get identity plus linear terms. We're going to get now quadratic terms. We get this guy can even put it together because it's the same TAB if we want. Okay, plus quadratic terms coming from these guys. Already a mistake? No? Okay, plus quadratic terms coming from these guys, so we get minus. This one with this guy will be phi 1a, phi 2, let's call it b, ta, tb. Okay? That was easy. Now comes a more difficult part. This friend over here, because we know that this should be the identity plus I phi a. Sorry. GA of phi 1, phi 2, TA plus a half GA phi 1, phi 2, GB of phi 1, phi 2, TAB. Okay? Now, what is our function? It's over there. On the top there, we're supposed to plug that in here. Okay? So we're supposed to get the identity plus I. So we just use our function. Is phi 1 of A. It's good that many terms ended up being 0. Plus D, A. So these two indices are anything. So let's call them E and F if we want. Phi 1 E, phi 2 F. Okay? That's this G that depend on A, TA, plus a half. Now comes the tricky part, okay? So we need cross terms and everything. Let's just write it as phi 1A plus phi 2A plus DA, again, EF, phi 1E, phi 2F. Okay? Now the other one is phi 1B plus phi 2B plus BB. Let's call them M and N. Phi 1 M, phi 2 N times TAB. Okay? So who is done? Can anyone tell me if I come? Well, first of all, let's try to see. Okay, I'll do the first two, then you do the third order term. So I'll do the identity. So let's compare this side with that side. Okay? Well, the identity works out here and here. So I'll do the linear term, and then you would do the quadratic term. So let's look at the very difficult linear term. The quadratic term is easy. So let's look. Here we have this term. And surprise, here we have the term 2. So we're done. And this term coincides with this one. Okay? I did my very difficult part. Okay, I'll even do one more. Okay? Two more. I'll do this quadratic piece. Okay? Phi 1, phi 1. Let's see. Well, where do I get phi 1 from? I get it from here. Okay? These two guys will give me a contribution. And that contribution is identical to this contribution. So I can cancel this quadratic term. And remember that the quadratic term is done. Phi 2 will also cancel. Okay? So I'm only left with DA, EF, phi 1E, phi 2F, plus, so I have to take care.
Sorry.
Yes?
Multiplier I in the body.
Thank you. That's very, very important. So here we get, now, this is interesting, right? Because phi 1 with anything here will give us cubic terms, so we don't care about them. So the only contribution that we get is phi 1a with phi 2b, TAB, plus a half phi 2a, phi 1b, TAB. But remember, sorry, this would be, yeah. But remember that this is symmetric in its labels. So we can combine this whole thing as a single term, phi 1a, phi 2b, TAB, absorbing the half. So we are done. Yes, thank you, very good. Excellent. Okay, so everybody else, you should also feel free to correct me. Don't be afraid to tell me that I'm missing terms. Otherwise, we won't get to the conclusion. Okay, so we're almost there. And here is the conclusion. The conclusion is that if we compare both sides, we should get from that side, we learned that we have TATB. Okay, so we are comparing coefficients of the corresponding terms, phi 1a, phi 2b. On this side has to be equal. Well, so yeah, so we'll have to reshuffle the indices a little bit because we need a and b here, right? So let's do something like I, B, C, A, B. Sorry? Yes. DC, very good. Plus, so the last one is easy, is TAB. Okay? Very good. So we get this equation. And it basically tells us that the second order term is determined completely in terms of the first order term if we only knew what these d's are. Okay? But what else can we learn from here? Well, let me write this equation slightly differently. Let me write it as, well, not even, yeah. Let me use the fact that this is symmetric. Okay? And write exactly the same equation, but with the labels exchange. Okay? Somehow, I want to get information about these without having to worry about the second order term. I don't want to worry about TAB. But we know that TAB is symmetric, so we can replace this by AB. Remember? Just from the symmetry property, we can swap the indices. Now, if we multiply this by a minus sign, so let's multiply by a minus sign, the whole equation. Okay, that's what I'm going to do. And then add up the two equations. So you get a plus sign, minus sign here, and minus sign here. Now I'm going to add up the two equations and find here something that looks like TBTA minus TATB is equal to I DCAB minus DCBA times TC. And this cancels out. So we get something interesting. We get a relation between only the first order operators we had, okay, and these real numbers D. So there is actually a nice way of writing this. Yeah, for some, yeah, this is going to look like being very, very silly, but I actually don't like the big first. So I'm going to exchange. So I'm going to multiply by -1, so the whole thing. Yeah, that sounds like a, sorry, it's just, somehow the lexicographic order, there is something interesting about it. So I'm going to write it as DC BA minus DC AB DC. Now I like this equation. Yeah. Let me define this object that depends on these indices and which is antisymmetric in A and B. You see, we didn't have any antisymmetry properties before for D. Now, but we only have the antisymmetric combinations of D. And that, let me give it a name, remembering that this object has the property that is antisymmetric in A and B. Okay? I'm going to put an I here that comes from here. And now this combination of operators has a name. What's the name? It's called a commutator, okay? Because it measures the failure of commuting, right? So if you want to know if two operators commute, you multiply, you apply one first and then the other, and then you apply them in a different order, and you compute the difference. So the commutator is what measures the failure of two operators to commute. All right. Now you see that all the structure of this, of the group very near to the identity, is controlled by this set of numbers, this set of real numbers, and these are called the structure constants. And we're almost done. With what we want to do today. Because now we can say the following. Something that you learned from Anna's course was that there is another algebraic structure that is interesting, right? Apart from groups, we can also have what? You also learned about algebras, right? Now, could this set of operators, TA and TB, define an algebra for you? They almost look like they want to define an algebra. But there is a slight problem here, and it's the following. In order to define an algebra, what do you need? You need a vector space. So it could be the vector space of Hermitian operators. That's a vector space, right? Very good. Now, what else do you need? You need a product, right? But the product is something that maps two elements in the vector space to a linear combination of elements in the vector space, right? Which is also an element in the vector space. But you see here there is something funny. If we define this as the product, okay? Here we have to be careful because these operators have another product structure here, right? But this product structure, TA composed with TB, cannot be written as a linear combination of just nice operators. So this is not what defines our algebra. This one has a good chance because the commutator, if we define this as the product, it seems to be written as a linear combination of the same guys. But there is this I there, okay? So is this operator, these guys are real. Is this Hermitian? It's not Hermitian, okay? So we just have to fix that a little bit. So let me define. Otherwise, Anna will be upset because all her work will not lead to anything. So we want to get an algebra. So let me define T hat A to be minus I T A, okay? So if we do that, and we use that relation, we find that TA hat, TB hat, is equal to FCAB, TC hat. Okay? Now, these operators are anti-Hermitian, but okay, now we have a vector space given by our TA hats, or generated. So this will be called the generators. It's generated because they provide a basis of this vector space. Okay, the basic basis vectors are called the generators of this algebra. And we have the product, TA hat star TB. Okay, now this star is not the composition of operators, right? In fact, we don't even have to talk about these as being operators. We can think about this as a general vector space. And we have TA and TB. We define a product. And this product is defined to be a particular linear combination called or given by these numbers and elements in the algebra. Okay, now this is an algebra. What kind of algebra this is? So is it commutative? Well, in order to know if something is commutative, we just have to, once again, test whether this is true or not. But now we can go back to our definition. Yeah, sorry. Yeah. But now we can go back to our definition and realize that this is antisymmetric in these labels. And we find that in our algebra, in fact, what happens is that this is equal to minus TB. So the answer is no. Now, is it associative? Who thinks it's going to be associative? Almost everything I know is associative, so it could be. Who thinks it's associative? 1, 2, 3, 4, 5, 6, 6. Who thinks it's not associative? 1, 2, 3, 4, 5, 5. OK. Who thinks it's anti-associative? There must be some other options, because not everybody. OK. Well, there is only one way to find out. If you wanted to know that something is commutative, you compute the commutator. If you want to know if something is associative, you compute what? The associator. Of course, what else would you compute? Right? Is it associative? OK. Well, let's do it. What do we have to compute? This is a test.
Sorry, your second term doesn't make sense.
Thank you.
I guess
No,
this
I mean-
Still?
doesn't make-
Oh, of course this is 0. Yeah, so I erased the wrong one. Yeah, I erased the right one. Good. This is what we want to test. Right? If this vanishes, then our algebra is associative. Well, there is only one way to find out. Let's just do it. Now here we're going to use much more than this. Right? For any f's, any crazy f's that you come out with, which are antisymmetric in AB, okay, it's not true that we're going to get something that reproduces a structure that comes from operators and this structure of a commutator. Okay? So in order to find out whether it's associative or not, we actually have to go back and get more information than these f's, which comes from the fact that this is a commutator. Okay? So let's actually go back to that definition and use the commutator here. So what is this? This is the commutator of TA with TB with the commutator of TB TC minus the commutator of TA TB. You thought that I was going to get it wrong, but no. This is what we want to compute. Okay? So we ran out of time. So there are two options. Either I can tell you what the answer is or wait until tomorrow. Or you can naturally do it. Well. OK. It's an exercise to do it, okay? Exercise. Find out what goes here. Once you find out what goes there, okay, this is something very simple, right? You just do it in terms of, the idea is to expand out everything, right? All the commutators explicitly in terms of compositions of operators. And see if you can recast that. First of all, you have to check that if they cancel or not. If they cancel, there is nothing else to be done because it's 0. If it's not 0, try to recast it again as something that looks in terms of this product, okay? We want to find out what is this in terms of this product, the product in the algebra, okay? This product in the space of operators is a crappy product that we don't like. We don't want to think about that product, okay? That's only an auxiliary product that we have sitting there in the back of our minds. The nicest product that we want to deal with is this star, okay? In the algebra. That's the product in the algebra. So whatever happens to be here, we want to write it in terms of this product. Once you do that, okay, look at the formula you got and translate this into a condition on this set of real numbers. The reason is that if somebody comes and tells you that this is going to generate a Lie group, okay, or this is how a Lie group is going to be controlled around the identity, you can check whether that's true or not by checking that these FABCs will satisfy the identity that follows from here. So let's write what the identity is, or the condition, in terms of FABCs, just for these two terms, and you will do it for whatever you find here. So let's see. We can replace this commutator by F, E, BC, T, E, okay? And then we get something that looks like F, E, BC commutator, T, A, T hat, E, which by itself, this piece is again given in terms of these guys. So let me call it G, AE times TG hat, right? That's this term. That's the first term. We can also do the same thing for the second term. So do the same thing for the second term. And write the condition on F's as a quadratic equation on F's, okay? So clearly, you will go, the idea is to collect every term, all the terms that comes with the same T, and you will get a condition that looks like products of F's, 2F's coming from the first term, minus 2F's coming from the second term, and something coming from the mystery term, okay, that you will find out. Now, what's going to happen is that if somebody comes with a set of F's and declares that this is a product that defines something that will generate an algebra that will generate a group, or an algebra that's what you get by looking at a Lie group near the identity, you can tell that person whether he's right or not by checking that the set of F's that this person gave you satisfies this identity. Okay? This has the name of a very famous mathematician, but we're going to talk about that tomorrow. Okay? Any questions?
What's the reason for defining a TA hat? Is it because the structure, we assume the structure constant to be real?
Yes, that's the reason.
Probably repeat the question.
Yeah, okay, very good. So the question is, why did I bother to define these T hats? And the reason is that in the previous definition, I assumed that the F's were all real, right? If they are all real, then the commutator relations that I had before would imply that the product of the operators without the hat would end up giving me a linear combination of objects that were not in my vector space, right? Because the original operators were Hermitian, and then it would express this product of operators as a linear combination with the I here of anti-Hermitian operators. So a trick was to define this new object so that this product maps the same vector space, the product of two copies of the vector space, into the vector space itself, because I'm declaring that my vector space is over the reals. Okay? Very soon, we will relax that condition and work over the complex. Then everything that we're saying here will not be very relevant. But yeah, I shouldn't have said that. Okay, any other questions? Yes?
Can we assume that DAB is antisymmetric in AB without loss of generality? Because we seem to use only their, well, subtraction of DAB minus DBA.
Well, you see, the Ds, we cannot tell anything about the Ds, right? The Ds are just objects that come from the Taylor expansion, and they multiply functions of phi 1, phi 2. So there is no antisymmetry. We cannot tell anything about the Ds.
We seem to use only the just F in algebra.
Well, the F, remember, the F ended up being equal to the antisymmetric combination of the Ds, right? So the F, by construction, ended up being antisymmetric. So the Ds didn't have to satisfy any properties. So we had that F was something like this. DVC minus VCB. Okay? Remember that Ds didn't have to satisfy anything. It was along the derivation that we ended up with something antisymmetric. Oh, yes, there were two more questions.
Is it true that if we have a set of Fs which satisfy the last two properties, then there's going to be some Lie group for which we self circumstance?
Yes. And this will be called a Lie algebra. Yeah. So your job is very, very important. You should find out what the condition is for these Fs to define a Lie algebra. Okay? There was another question?
Well, I was just wondering, then why did you put an I in the first order integral expansion if you are going to reabsorb it afterwards?
Very good. That's a very good question. And the reason was that I wanted to make my big statement about Hermitian operators.
Yeah, but you can make it anyway, or no?
No, if I don't put the I, then the T's will not be Hermitian, right? Right. So it's just convention. It's just because I wanted to make a statement about Hermitian operators. Okay. Yep. One more.
I think GRN of R is not connected back to the beginning of the lecture. Because you have determinant greater than 0 and less than 0.
But you can connect that continuously because you allow any determinant, right?
I said GRN of R, so everything.
Oh, of R. Oh, I see. Sorry. As I said, very soon we're going to be thinking about everything over the complex. So over the complex is fine.
Okay.
Yeah. Sorry, I didn't understand that. Yeah. Any other questions? Yeah, but for today and tomorrow, let's keep everything over the reals. Okay?